morning viewers, welcome to KU Band live lecture on earthwork calculations. Today in this session we shall discuss about the following topics in earthwork calculations. In earthwork calculations we shall discuss now about the introduction to earthwork, formation level of a road for plain country, formation level of a road for hilly country, the cross section of a road in cutting, the cross section of a road in banking, earthwork in canals, calculation of area of cross section of a canal or a road, and the methods for calculation of quantity of earthwork. Now let us discuss about these topics each one by one now. Almost all civil engineering projects involves the earthwork, that is either for example roads, railways, canals, earthen dams, tank bunds, etc. Either the earthwork in excavation or in filling, both are used for forming a level. Here the earthwork in filling is commonly referred to as earthwork in embankment. When we use the term earthwork in embankment, it is nothing but the earthwork in filling. Next, the earthwork in excavation. The earthwork in excavation is commonly referred to as earthwork in cutting. When we say that the earthwork in cutting, that is nothing but the earthwork in excavation. Basically, the earthwork is computed from length, breadth and depth of excavation or filling. There is, for any civil engineering project, it is necessary to know what is the level of ground or where is the formation level. Now let us see the formation level of a road or a ground. This visual shows the formation level of a ground. This is the curved line is the reduced level of the ground. This portion is filling, earth in filling, and this is the earth in cutting. Again filling, cutting. Practically when we see the earth is not, the level of the ground is not horizontal, not plane. It is always undulations, it is having some undulations. This is the general formation level of a ground. This is the reduced level of a ground. Now let us see the formation level of a road for plain countries. For a plain country, this is the ground level which is horizontal, and this is the formation level. That is, the formation level is considered to be as plane in case of plain countries. That is, it is a level, there is no cross slope. This formation level is fixed considering the flood level, height of bank, depth of cutting, gradients, etc. So generally when we take for a plain country, the ground is considered or assumed to be a level surface. Similarly, the formation level is also a level surface. Now let us see the formation level of a road for a hilly country. For a hilly countries, the road may be, that is the topography of the ground may be either sloping downwards or it may be sloping upwards. Generally in case of hilly countries, the nature of the ground may be either in banking or in cutting. So the quantity of earthwork which is there, which we excavate from the excavation, that is from cutting, we use that earthwork for banking purpose within the economical limits for the construction of the project. Now here we can see the formation level of a road in case of hilly countries which is sloping downwards, and here we can visualize here the formation level of a road sloping upwards in case of the hilly countries. This is how the formation line is fixed. Now, let us see the cross section of a road in cutting. Here we can visualize the cross section of a road in cutting. The cross section of earthwork of a road in cutting or in banking is in the form of a trapezium. Here we can visualize this is the ground level and this is the top width or width of the road in cutting. N:1 are the side slopes of the road in cutting. Let B be the depth of the road in cutting and D is the depth of cutting and B is the breadth of road in cutting. This is the cross section of a road in cutting. Now, let us visualize the cross section of a road in banking. Here we can visualize the cross section of a road in banking. The cross section of a road in cutting or in banking is in the form of a trapezium. This is the ground level and this is the cross section of a road in banking, where B is the top width of the road in banking and D is the depth of the road level above the ground surface, and N:1 are the side slopes of the cross section of a road in banking. Now, let us see how to calculate the quantity of earthwork for the cross section of a road in cutting or in banking. The quantity or volume is nothing but the sectional area multiplied by the length. What is the sectional area? The sectional area of a trapezium, because the cross section of a road in cutting or in banking is in the form of a trapezium. It is the sectional area. The sectional area is nothing but the area of central rectangular portion plus the area of side triangular portions. As we have seen just now about the form of cross section of a road in cutting or in banking, it is a trapezium. The central rectangular portion plus the area of side triangular portions. So, the area of rectangle is breadth multiplied by the depth plus there are two triangles in a trapezium. So, 2 into area of a triangle is half into base into height, that is where D is a depth, that is equal to BD plus N into D square. This is how the sectional area of the road cross section of a road in cutting or in banking is calculated. So, how to calculate the quantity or volume of earthwork? The quantity or volume is nothing but the sectional area multiplied by the length of the section. Sectional area multiplied by the length will give the quantity or volume of earthwork for the cross section of a road either in cutting or in banking. Now, let us see the cross section of a road of a canal. That is the earthwork in canals. As we have seen just now, the cross section of a road in cutting or in banking. Now, let us see about the canal sections. There are 3 cases for canal sections. Case 1 is earthwork fully in excavation. Case 2, earthwork excavation partly in cutting and partly in embankment. And third case for the earthwork in canals is earthwork fully in embankment. Now, let us discuss about these 3 cases each one by one. In this visual, we can see the cross section of a canal fully in excavation. Just now we have seen what is this excavation. Excavation is nothing but the cutting portion. The cross section of a canal fully in cutting. When you say that the canal is in excavation, that is when the ground level, this is the ground level, and here this is the bed level of the canal. When the bed level of the canal is completely below the ground level, then you will say that the section is completely in excavation. That is, the canal section is completely in excavation. If you take that, if B is the breadth of the canal in cutting and D is the depth of the canal in excavation or cutting, and n is to 1 are the side slopes. Then how to estimate or calculate the quantity of earthwork for the cross section of a canal in excavation? Let us see now. The quantity of earthwork is calculated on the same principle of a road estimate. That is, just now we have seen how to calculate the cross section earthwork for a cross section of a road both in cutting and in banking. Similarly, the cross section of a canal is also a trapezium. So, the quantity of earthwork in excavation is nothing but the sectional area multiplied by the length. The sectional area of a canal is BD plus n into d square multiplied by the length of the section, where B is the width of the canal, D is the depth of the canal, and n is to 1 are the side slopes. D is the depth of the canal. This is how we calculate the quantity of earthwork in when the cross section of a canal is completely in excavation or completely in cutting. Now, let us see the second case for the earthwork in canals. Earthwork excavation partly in cutting and partly in embankment. Here, this visual shows the cross section of a canal partly in excavation. This is the excavated portion, and partly in banking. These are the banks on either side of the excavation. If suppose D is the small d is the depth of the canal in excavation and small h is the height or height of the banks above the ground level, and B1 and B2 are the top widths of the banks, N1 is to 1 is the inner slopes of the banks, N2 is to 1 are the outer slopes of the banks, and N is to 1 is the side slopes of the canal in cutting. So, how do we calculate the quantity of earthwork when the cross section of a canal is partly in cutting and partly in embankment? That is, we have to calculate the sectional area of the cross section of a canal partly in excavation, that is this portion, plus the sectional area of the canal partly in embankments. After calculating the sectional areas multiplied by the length of the sections will give the quantity of earthwork that is required when the cross section of a canal is partly in cutting and partly in embankment. The height of bank, that is capital H, from the bed of the canal is generally same throughout. That is, the total height from the bed of the canal to the top of the banks is capital H. It is denoted as capital H. It is considered to be same throughout. The height of the bank H above the ground level is, it may be found as follows. That is, the height of a bank is nothing but the total height from the bed of the canal to the top width of the canal minus the depth of the canal in excavation. The side slope of excavation n is to 1 and inner side slopes of banks n1 is to 1 are given in such a manner that in due course both will attain the same slopes. That is, the side slopes n, n1 and n2 may be same or different. So, the slopes we have seen it, that is n is the inner slopes of the earthwork excavation partly in excavation, and n1 and n2 are the slopes for the banks, outer slopes as well as the inner slopes. They may be same or different. This is how we estimate or calculate the quantity of earthwork in excavation and partly in excavation and partly in bank. Now, let us discuss about the third case for the earthwork in canals. Case 3, that is earthwork fully in embankment. When the cross section of a canal is completely in embankment, we can visualize here the cross section which is completely in embankment. This is when you say that the cross section of a canal is completely in embankment. That is, this is the ground level of the ground level and this is the bed level of the canal. When the bed level of the canal is completely above the ground level, then we say that the cross section of a canal is completely in embankment, or we can say it, the cross section of a canal is completely in banking. This is the side slopes, outer slopes, and this is the inner slopes. If B is the width of the section and D is the depth, and we can calculate the total width of the section. How to estimate the quantity of earthwork when the cross section of a canal is fully in embankment? Let us see now. The quantity of earthwork may be calculated considering the whole as a solid and then deducting the channel portion. That is, considering the total as a solid section and then deducting the channel portion, we will get it is the capital D is nothing but small d plus h, where d is the total depth and small d is the depth of the channel portion plus dh is the height of banks. B, total width of the canal in embankment is nothing but small b plus b1 plus b2 plus 2n1 into d. So, the quantity of earthwork is nothing but the whole sectional area, that is, we are considering the total sectional area minus the sectional area of a channel. Sectional area multiplied by the length will gives the quantity of earthwork. Substituting the values for the sectional area for channel as well as for a solid, that is BD, B into D plus N1 into D square minus B into H plus N1 into H square multiplied by the length will gives the quantity of earthwork when the cross section of a canal is in embankment. This is how we calculate or compute the quantity or volume of earthwork when the canal section is completely in excavation, when the canal is partly in cutting and partly in embankment, and also the third case, that is when the cross section of a canal is completely in embankment. Now, let us see the general cross section of a canal when it is completely in excavation. This is the ground level. This is the bed level of the canal. N:1 are the side slopes of the canal. If small b is the bed width of the canal and small d is the depth of the canal in cutting, this is n into d and this is n into d. Now, before knowing how to calculate the quantity of earthwork for a canal or a road, we should know how to calculate or compute the area of cross section of a canal. Now, let us see how to calculate the area of cross section of a canal. Calculation of area of cross section of a canal. Let B is equal to width of the canal at the bottom and D is equal to depth of embankment or cutting. That is, since the cross section of a road or a canal is same, that is in the form of a trapezium, we are considering the depth of embankment or in a cutting. N:1 are the side slopes, that is n horizontal is to 1 vertical. The top width of cutting or bottom width of embankment is nothing but the total width at the bottom of the canal section, P plus 2 into n into d. So, computing the average width is nothing but the summation of the bottom width small b plus the top width, that is b plus 2nd. The average of bottom width and top width will give you the average width of the canal section. So, the area of cross section of a canal is nothing but the average width multiplied by the depth. The average width is b plus n into d multiplied by the depth of the canal is d. So, the area of cross section of a canal or a road is B into D plus N into D square. This is how we compute the area of cross section of a canal or a road. Now let us see how to calculate the area of cross section of a canal or a road taking a simple example problem. To find the area of embankment if the top width is 5 meters, that is the top width of a road is given as small b is given as 5 meters and the depth is 4 meters. The depth from the ground level to the top of the embankment is given as 4 meters, small d is 4 meters. So, the side slopes are 2:1. Here n:1 is given as 2:1. So, how to compute the area of this embankment, road in embankment? Let us see now. Just now we have discussed that the top width is given as given data 5 meters, the depth of the embankment from the ground level is 4 meters, side slopes n:1 are given as 2:1. So, the formula for calculating the area of cross section of a canal or a road is B plus N into D into D. Substituting the above data or the values from the given data, we get the required area of an embankment. This is how we compute the area calculation for a road in embankment. Now let us see one more example for a canal section. To find the area of cutting if the bottom width of a canal is 3 meters and the depth is 2 meters. The side slopes are 1:1. The following visual shows the cross section of a canal in cutting where the bottom width is given as 3 meters and the depth is given as some 2 meters. So, this is the ground level and the side slopes n:1 are given as 1:1 where n is equal to 1. Now, substituting the above data, we can compute the area of a canal in cutting. The given data is the bottom width of the canal is given, the depth of the canal is given, the side slopes are given. So, the area of cross section is nothing but B plus ND into D, where B is the width, N is the side slope, D is the depth of the canal in cutting. After substituting the above values from the given data, we can compute the required area for the cross section of a canal in cutting. This is how we compute the area of cross section for a road or a canal either in cutting or in banking. Now, let us see what are the various methods for calculation of quantity of earthwork. The calculation of earthwork either in excavation or completely in banking may be calculated by the following methods. They are, the first method is Midordinate Rule or mid-sectional method. The second method for calculating the quantity of earthwork is mean sectional method. The third method for the calculation of quantity of earthwork is trapezoidal rule. The fourth one for calculation of quantity of earthwork is prismoidal rule. These are the various methods for estimating the quantity of earthwork. Now let us discuss about these methods, each one by one. Method 1, Midordinate Rule or mid-sectional method. In this method, when the ground is in longitudinal slope or the formation has uniform gradient for a length L, then the average depth is found at the midsection. Midordinate rule means the average depth has to be found at the midsection. We shall see in the following visual now. This is a longitudinal section of a road, that is, if D1 is the depth of a road or a canal at first section, say this is A, and D2 is the depth of the canal or depth of banks at the other end. So, if D1 and D2 are the depths and B is the width of the road, so we have to calculate the area, or first of all we have to calculate the average depth of cross section, that is mean depth at the midsection. Let us see how to calculate it. So, the quantity of earthwork is computed as follows. Let D1 and D2 be the depths of bank at two ends. So, the mid-ordinate or average depth dm, that is nothing but the average of these two depths D1 plus D2 by 2. The area of midsection AM is nothing but B into dm, where dm is the average depth plus n is the slight slope, n into dm square, that is average depth square. So, the quantity of earthwork between the two sections by using midordinate rule is calculated as volume or quantity of earthwork is equal to area at the midsection multiplied by the length between the sections, that is equal to B into dm plus n into dm square multiplied by L. This is how we compute the quantity or volume of earthwork between the two sections by using the midordinate rule. So, after getting the above values or the results, they have to be tabulated in the tabular form by using the midordinate rule. This is the first column is the chainage, next is the depths or heights in meters, this is the mean depth or height, this is the area of the central portion, area of sides, and this is the total sectional area, which is summation of area of the central portion plus area of the sides, and the length between the sections is designated as L in meters. So, the quantity is nothing but the total sectional area multiplied by L, which is either in embankment or in cutting. Now, let us solve a simple problems how to calculate or compute the volume of earthwork by using mid-sectional method. Let us take a simple problem. A canal is proposed to be excavated between 2 points A and B 100 meters apart. That is, the distance between the 2 points A and B is taken, L is given as 100 meters, and if the bed width is 10 meters, small b is given as, the bed width is given as 10 meters. Side slopes 1.5:1, that is n is to 1 is 1.5:1. N is nothing but here 1.5, and the depth of cutting 1 meter and 3 meters at A and B, that is D1. Suppose we have assumed that D1 and D2 are the depths. D1 is nothing but here 1 meter and D2 is 3 meters at A and B respectively. Now, it is required to calculate the quantity of earthwork in excavation by mid-sectional area method. That is, by using mid-sectional area method, we have to compute the quantity of earthwork. Let us see now. From the following visual, it is clearly shown, this is the end A and this is the end B. The length between these two ends A and B is given as 100 meters, and the depths at end A, first section, is given as 1 meter. Similarly, the depth at the other end is taken as 3 meters. So, we know D1 and we know D2. Let us see how to compute. This is dm, where dm is nothing but the average depth of the sections, which is nothing but the average of the depth at first section and depth at second section. Let us see how to compute it. This is the given data for the given problem. Now, how to compute it? The average depth we have to compute it, that is dm is nothing but the average of the two depths d1 and d2 by 2. So, we get sum in meters, the average depth in meters. After getting the average depth, the average sectional area has to be found out. Average sectional area is nothing but b plus n into dm multiplied by dm, where dm is the average depth. Substituting the above values, we get the average sectional area in square meters, since area is expressed in square meters. Now, the volume of earthwork is calculated by using the formula average section area multiplied by the length between the sections. As we know that length between the sections is already given as given that 100 meters. We have got here the average sectional area. Average sectional area multiplied by the length, we get the required volume of earthwork in cubic meters. The volume or quantity of earthwork is usually expressed in cubic meters. This is how we compute the quantity or volume of earthwork by using mid-sectional method. So, after getting these results, we have to tabulate in the tabular form by using mid-sectional area method. Let us see. Before that, the visual shows the cross section of a canal at 3 sections. This is the cross section of a canal at first end A, where the depth is 1 meter. This shows the cross section of a canal at B, and this is the cross section of a canal at C. That is, at C, it is nothing but the average of the 2 sections. Now, let us tabulate the following results in the tabular form. Chainage 0 and the length between the sections is 100 meters. So, the chainage is taken as 0 and 100. Depths or mean depths D1 and D2 are taken. The mean depths is calculated. After that, the sectional area of the central portion is computed, B into D, and the area of sides is N into D square. The total sectional area is sum of the central portion as well as the sum of sides. The length between the sections is given as 100 meters. The quantity is estimated as the average sectional area multiplied by the length will give the quantity of earthwork in cubic meters. Now, let us solve one more problem by using mid-sectional area method. The depths at two ends of an embankment of a road of length 80 meters are 2 meters and 3.4 meters respectively. That is, the length between the two sections is given as 80 meters. That is, the length is given as L is equal to 80 meters and the depths 2 meters and 3.4 meters. D1 is 2 meters and D2 is 3.4 meters. The formation width and side slopes are 12 meters and 2:1. That is, the formation width is nothing but the width of the road section. B is equal to, small b is equal to 12 meters and n is to 1, that is, side slopes are given as 2:1, where n is equal to 2. Now, it is required for us to calculate or compute the quantity of earthwork by mid-sectional area method. Same thing, this figure shows the cross section of a road where D1 and D2 are the depths at two ends. We have to compute the DM, that is mid-sectional depth. After computing it, we have to compute the mid-sectional area. After computing the mid-sectional area, the volume of earthwork is taken as mid-sectional area multiplied by the length will give the volume of earthwork by using the mid-section area in meter cubes. After getting the above results, they have to be tabulated in the tabular form as follows. This visual shows the tabulations of the above problem for a road, for estimating the quantity of earthwork in a road in embankment, which is estimated to be in cubic meters. Now, let us see these. What are the applications of this midordinate rule? Where it is applicable? The mid-sectional area is the area of cross-sectional at the midpoint of the distance between the sections. This method gives accurate results when the ground is fairly level. However, since the ground usually has a large number of ups and downs, this method is not generally used. That is, the midordinate rule is only applicable only when the ground is level. But practically, when we see the ground is not level, it is having undulations. This method is only used in case of plain countries. This is how where the Midordinate Rule is used. Now let us see the second method for estimating the quantity of earthwork, that is mean sectional area method. This mean sectional area method is also known as the average sectional area method. In this method, the volume of earthwork is computed as follows. The volume of earthwork is nothing but the mean cross sectional area multiplied by the distance between the sections. If A1 and A2 are the area of cross sections and AM is the mean area of cross section, where A1 is the area of the section at one end, that is B into D1 plus N into D1 square, where D1 is the depth at the first end and A2 is the area at the second end, that is B into D2 plus N into D2 square, where D2 is the depth at the second end, that the other end of the canal or a road. So how to compute the volume of earthwork? The volume of earthwork V is nothing but the average cross sectional area multiplied by the length will give the quantity or volume of earthwork by using the mean sectional area method. This is how we compute the volume of earthwork by using the mean sectional area method. This visual shows the how to compute the longitudinal section of a road. This is A1, where A1 is the area of cross section of a road at one end of the road, and this suppose A2 is the area of cross section at the other end. So we have to compute the mid sectional area. After computing the mid sectional area, the quantity or volume of earthwork is nothing but the mid sectional area multiplied by the length between the sections. This is suppose this is end A and this is end B, where A and B are the two ends of the road. That is, if L is the distance between these two ends, so the volume is nothing but the sectional area multiplied by the length will give the quantity or volume of earthwork. This is how we tabulate the results after getting the calculated from the it should be entered in the tabular form for mean sectional area method. Now let us see a simple problem how to calculate the quantity or volume of earthwork by using mean sectional area method. The same problem just we have done for mid sectional area method. A canal is proposed to be excavated between 2 points A and B 100 meters apart, that is the length between the two ends of the sections, that is capital L, is given as 100 meters. If the bed width of is 10 meters, the canal width is small b is 10 meters and side slopes are 1.5:1, that is side slopes n is to 1 is given as 1.5:1, where n is equal to 1.5, and the depth of cutting 1 meter and 3 meters at A and B. If d1 is equal to 1 meter and dt is equal to 3 meters at A and B. So now it is required to calculate the quantity of earthwork by mean sectional area method. Let us see now. This visual shows the longitudinal section of a canal where d1 is the depth of 1 meter at end A and d2 is the depth of 3 meters at the other end B. It is required to calculate first of all the mid that is dm, where dm is the depth, average depth at the two sections. Let us see how to compute the volume of earthwork or quantity of earthwork by using mean sectional area method. So the area of cross section at one end A is nothing but A1 is equal to B into D1 plus N into D1 square. After substituting the given data, we get the area of cross section at one end in square meters. So the area of cross section at the other end is taken as A2 is equal to B into D2 plus N into D2 square. A2 is equal to, we get the area in square meters. This shows the cross section of a canal at one end A, where depth is D1 1 meter, the cross section of canal at B, where depth is 3 meters, and the cross section in this cross section of a canal at midpoint, that is midpoint of A and B, that is C, where depth is 2 meters. So after computing the area of cross section at end 1 and end B, we can calculate the average area of cross section to be the average of the two areas A1 plus A2 by 2. We get the required area, that is AM is the average area of cross section in square meters. So the volume of earthwork in cutting is given as V is equal to AM into L. AM is nothing but the average area of cross section multiplied by the length will get the required volume of earthwork in cutting. After getting this, we have to tabulate the results in the tabular form using mean sectional area method. So there are also two more methods for calculating or computing the volume of earthwork, that is trapezoidal method and prismodal method. So till now we have seen what is the nature of ground, what is the formation level, how it will be for plain countries, then for hilly countries. For plain countries the formation level is a level ground, and for hilly countries it may be sloping upwards or it may be sloping downwards. So the first of all, in order to compute the volume of earthwork, we should know how to compute the area of cross section of a canal or a road. It is usually in the form of a trapezium. So the methods for computing the calculation of volume of earthwork, we have discussed about the mid sectional area method and mean sectional area method today. In mid sectional area method, it is applicable only when the ground is for level ground. Mean sectional area method, we can use it. Now in this next session we shall discuss about the next methods for computing the volume of earthwork, that is trapezoidal method and prismodal method. It shall be followed in the next section. We shall end this session for this today.